start with convolutional neural networks. So in this lecture, we'll see like what are the different basic like building blocks of convolutional neural network, and like what's the fundamental operation which is being performed inside these networks. And then we'll also have like a case study. So in the agenda we have, first we will talk about like the overview to give you like some high level idea where these CNNs are used. And then we'll try to go through some of the basics which we have already covered like in the past lectures, but which is relevant to this topic. And then we will directly jump into the fundamental operation, which is the convolution operation, or you can say correlation operation. And then some practical considerations, like some things which you should be aware of when you're designing a neural network. And finally, a case study where we'll take like a well-known CNN architecture and try to understand like how it works and what are the different components there. So let's start with the first segment, which is the overview of CNNs. And before that, like some very interesting example to you. This is just a joke, so not part of the lecture. So these days, like when you're working on deep learning, usually like it's very fascinating, right? A lot of people, I mean, they're very interested, and most of the fields are actually interested in this area, and they're trying to use deep learning into their research. Okay, and for the general society, it's like a very big deal, like the kind of impressive results we have. And so this is just like interpretation, what different segments of the society thinks about like when you're working on deep learning. And this is also interesting because the deep learning job market, it's so hot. When you will see like when you graduate, like it will give you like very high paying jobs, and the job market is really good at this time. And other scientists, I mean, they might not be like getting that much of like in terms of salary. And this is also interesting because mathematicians, like everything they do, it's like well grounded in theory. But you will see like in deep learning, when you design your networks, when you train your networks, of course we have like some kind of mathematical background, but most of the time there are a lot of heuristics involved, so a lot of hit and trial. So that's one of the like limitation of deep learning at this point, and a lot of researchers are actually working on grounding like whatever findings we have, the interesting findings, to some kind of theoretical background. And if you think of yourself, you know, and this is a very famous scientist, Jan LeCunte, so you think you're doing something great, but actually most of the time, you will see in the programming assignment as well, you're just using existing code, right? You will see like if you use PyTorch, you're just importing like different library functions. And even for training, you don't have to write a lot of code. So basically, it's not like a lot of effort, but this is a different perception, like different segment from the society has. Now, another motivation for you, I think some of you might have seen like this in the news articles. In one of the like art contest, someone actually created this image using AI. And this was, I think, some version of DALI model. And this actually won the prize. And the artists were really not happy about this because, I mean, even though this looks really nice, but I mean, no one created this, right? It's just like AI generated. So something to think to think about, but this is exciting. And these days you will see like a lot of people are actually trying to do that. They are creating these arts and they are selling them online, and they are sometimes getting paid a lot. Okay, so that's one aspect. But if you look at like the results, I will show you like one simple example. And the problem here is, given a video, just a monocular video, can you estimate the depth of each pixel? And the problem says like, in this video, like whatever pixel you choose, can you tell like how far that pixel is from the camera or the camera viewpoint? And I will show you example like a CNN-based model can actually do a pretty good job. So the animation on the right, it shows like the depth of each pixel, and you can see like if you compare that with the input video, it's actually doing a very good job. And with like so there are a lot of applications of this depth estimation. One interesting application you can see is like you can actually create a stereo effect, because if you have these sequence of frames and you know like depth of each pixel, then at like certain time step you can actually kind of extrapolate or predict like what are the hidden pixels, because you know the depth, right? So this is again just one example or one application of depth estimation. There are a lot of others as well. So I think this is a pretty cool example to show like how powerful these CNNs are. Some more motivation. This is like the problem is super resolution, and the idea here is given an image which is like very bad resolution, which I'm showing you on the left. But you can see it's a very pixelated image, and you can use CNNs to actually convert it to a very high resolution image. So the input is on the left, and on the right it's like as the model is being trained, how the noise is actually being converted to the high resolution image. And you can see like the final result, it's really amazing, the quality of it. Okay. Now, so that's, I think, a lot of motivation for you. Now let's try to understand and get an overview of these CNNs. So these again are a class of neural networks. The difference is they will take images as input. And I'm saying mostly because they might not take images, they might take something else as well. Okay. And what they will do is, given that image as input, they will make predictions about that image. And depending upon like what problem you're trying to solve, they will the prediction will change. If it's classification, they will say that, okay, if the class is present or not. It could be localization, then they will have to give the bounding box as well, and so on and so forth. A basic structure of a convolutional neural network will look something like this. And again, it will vary a lot, but most of these components will be there when you train or when you build your own convolutional neural network. Okay, so let's try to understand the components of this architecture here. This is the input. So this is the input image, and it could be grayscale image, it could be a colored RGB image. Depending upon that, it will have like, let's say 1 or 3 channels. And then another important parameter is the resolution. Okay, that will like what's the height and width of this image. That will define like how many pixels you have. Then the second layer, usually you can say the first layer is the convolution operation. Okay, the layer is not being shown here, but these arrows actually represent that layer. So this will be the convolution layer, and this layer will actually convert this image into some form of feature maps. Okay, if you remember, like in the previous lecture, I said you are going from volume to volume. So in this case, the input volume is this image, and the convolution layer is actually converting that to another volume, which are the set of feature maps. And don't worry about like what these feature maps are, how we get these feature maps. We are going to go into detail of that, like every bit of that. So at the end of this lecture, you will be able to understand like what we are trying to cover in this overview. Okay, so then you might have some kind of subsampling where you try to reduce like the number of activations or feature maps you have. And you will see I will use the words feature maps and activations interchangeably. So both means the same thing. Okay, it's actually corresponding to the data which is flowing in your network. So then if you do subsampling, then the size of these activations or the feature maps might reduce. And then again, you can have more convolution layers. Again, you will get like set of feature maps. Again, you can have subsampling, you can reduce it. Then eventually you will have a fully connected layer, which will give you the prediction. And this fully connected layer is actually the MLP, the multi-layer perceptron we were discussing earlier. Okay, so that is also a part of your CNN architecture. And again, it depends. Like some of the recent CNN architectures, you will see that you don't have this fully connected layer. But again, that's just a variation. So it's an option whether you want to use it or not. But the earlier CNNs, they used to have this fully connected layer to give the final prediction. Now, the CNNs are not like recently developed. And I think in late 90s, I think in 1998, the photo I showed you earlier, Jan Lukun. So they developed this layered architecture. And if you look at this architecture, it actually resembles the one I showed you earlier, right? Exactly the same thing. The only difference is we have a grayscale image. And again, that's due to like the computation power. Back then, we didn't have like the powerful GPUs, right? And you can see like the input resolution, it's just 32 cross 32. But rest, it's the same. I mean, you have the convolution layer, you get the feature maps. This is subsampling, you reduce the feature map, convolutions, again, some transformations. Okay. So whenever you are applying these convolutions, you're actually transforming your activations to a different set of activations. or you're transforming your input image to like some set of feature maps. So that transformation is going on. And that the transformation is nothing but like the linear combination, or you can say the filtering operation, which we have been learning like throughout this course. And we'll come to that. Okay, then we have this fully connected layers. And in this case, we have 2 fully connected layers, and finally like 10 outputs. You can see this resembles like the multi-layer perceptron, which we discussed in the previous lecture. So 10 outputs because I think it was developed for digits. So if it's digits, then 10 outputs. Of course, for characters, like you might change it to 26. Okay, so CNNs are not new. People have been working on this prior to this. The issue was back then we didn't have computation power. We didn't have enough data. So the first strong results, they came in 2012. And the architecture was called AlexNet, and we are going to do a case study on this architecture later in this lecture. So the reason was not like innovation in terms of architecture. AlexNet, in fact, used the same architecture which we are seeing here in Linux. Okay, so the only difference was the availability of data and the availability of computation, like a lot of computation power. Okay, so what happened in 2012 was there was a ImageNet or image classification competition, which used to be there like in computer vision community. It's still there. So this was called like a large scale visual recognition challenge, and researchers were like improving every year, maybe 1 points or 2 points. But in 2012, the error rate was improved by like almost more than 10%. So it dropped from 26 to 15. So the next best entry was 26%, which was not using CNNs. So this was like a big breakthrough. And that's when like the deep learning revolution started. And that was the architecture used in AlexNet. And you can see like it's almost same as what we saw in Linux. Okay, this is the input. And again, we are going to talk more this architecture in more detail when we do the case study. All right, so it started in 2012, but today, I mean, CNNs, they are used like everywhere in all the problems, right? And this we have covered in the first lecture as well. We saw that we use CNNs for classification, we use them for object detection, we use for semantic segmentation. And later in the course, we will talk about some of these architectures of these CNN architectures, which are very popular and very, very good in, let's say, object detection or object classification. And they can be used for image captioning. We have talked about style transfer as well. Now, earlier I said like images are used as input mostly. So what I meant is we can use like some other kind of modality as well. Okay, so we can use natural language as well as input to CNNs. And the idea here is, let's say we are doing text classification. So what we do is, if this is your sentence in some of the languages, okay, so a sentence will have a sequence of words. What we do is each word can be converted to a vector. And there are different ways to do that. We will not go into detail of that. So word to vector is one such algorithm which converts each word into a vector, let's say of 300 dimension. Of course, you can have like 100 dimension as well. So what you can do is you can convert each word into a vector. And for a sentence, if you stack them together, that's going to give you a matrix. And then you can, if this is a matrix, you can use CNNs. All right. You can use this for audio research as well. Audio is like just one-dimensional signal, but you can represent that one-dimensional signal as a spectrogram as well, which looks something like this. And once you have this like a matrix form of input, you can apply CNNs. So if you can convert your data to a matrix format, either 2D matrix or 3D matrix or 4D matrix, then you can use CNNs. Okay, so if it's audio, you can use 1D. And this audio is like, you can even like just take the raw signal. You don't have to even convert that to spectrograms. All right. So it will change the operation you are using. If it's a one-dimensional signal, you will use 1D convolution. If it's high dimensional, let's say videos, you will use 3D convolution. All right. For images, it's 2-dimension. So you use 2D convolution. So with that overview, I think next we will talk about the basics which we need. But before that, do we have any questions?
I have a quick question about Lynette. I
Yes,
noticed
please
that
go ahead.
the last parameter said Gaussian connections. What could you explain what that means?
Yeah, so these weights, I think they were regularized using some kind of Gaussian distribution, right? I mean, this was used like back then. These days, I mean, it's no longer used.
Oh, I
So
see.
I
So,
will say, yeah, don't worry about it.
okay, okay, thanks.
So these days, it's just like the fully connected layer, which we talked about in the multi-layer perceptron, right? Fully connected layers. We just use that.
Okay.
All right, so no question, it seems. So let's jump to the next segment. So we'll see like what are the basics which will be required to understand like these convolutional neural networks, and all these basics we have already covered. So I'll just give you a quick recap of this. Okay, so the general CNN architecture we have already seen. We have this input as image. We have convolution layers, subsampling layers, again followed by convolution. And again, we can have several of these layers. This is just one combination. And at the end, we have like fully connected layer, which will give you the predictions. Of course, you can have more than one fully connected layer. Okay, so that's the input. Now let's talk about the input. So input can be, again, it could be one-dimensional signal, 2D, 3D signal. So let's talk about images. Images, we know it's like you can store that as a two-dimensional matrix, and it will have like certain height, certain width, and for each pixel location, or you can say like this grid location, you will have some value. For grayscale, it will be just one value. If it's RGB, you will have three value. Okay, so usually we work on RGB images. In that case, you will have a volume which represents the image, and that volume will be like three-dimensional volume representing height, width, and the depth. So depth in color, in case of color images, will be 3. In case of grayscale images, the depth will be 1. Okay, so that will be your input to your CNN. The second part is the network itself, and this part is like the convolutional part of this architecture, which tries to learn, or you can say extract features from this input sample. Okay, so that's the whole role of this part of the architecture. And once you have these features, you can use those features to perform the classification task. All right, so let's try to understand how this part of segment is actually extracting features. For that, let's go back to filtering. Filtering, we have seen, given a filter and your image patch, you perform this linear combination, right? So if this is your image, this is your filter, it gives you some kind of response. And the idea was it's trying to do some kind of pattern matching. So whatever pattern you have in your kernel, if that pattern is present in your input image, you will get high activation. Otherwise, you will get a very low activation. Okay, so if this is your image patch, again, it's a very small patch of a big image, and this is your kernel, all you do is you perform filtering, which is just element-wise multiplication of these values, and you can just take the mean, and you can just add up those values. Okay, so this is the basic filtering operation which is performed inside your convolutional neural networks. Okay. So this filtering, I mean, you can have two variations. Either you can find correlation, or you can perform a convolution. We'll briefly talk about that, what's the difference. And the basic difference, like conceptually, we know that they are basically the same set of operations. The only difference is you have to like flip your kernels in both the axes to match convolution with correlation. Okay, so this is the basic correlation operation. It's just taking element-wise multiplication and adding up the values. And convolution is if you flip your kernel, then you can again perform the correlation operation. Okay, so you have two extra steps. And we talked about edge detection, where what we did is we have this Sobel kernel, which was, and you are also doing this for a programming assignment. And it's trying to, if you look at this filter, it's actually trying to find edges. That's what this filter represents, because the values are changing in the X direction. And in this one, the values are changing in the Y direction. Okay, so that was the algorithm for Sobel. But the idea is, again, you are just doing filtering here. And what you're doing is whatever filter you have, you're trying to find that pattern in your input image. If this pattern is present, your outer activations are going to be high. So that's the whole idea about this center segment of your convolutional neural architecture. You will have these kernels here. We'll talk about that later. So those kernels will try to find the patterns in the input image. Okay, and it's not just one step. You will keep finding that patterns as hierarchy. So you'll find patterns in the input image, and then you'll try to find patterns in those patterns, and you keep doing that. So that's kind of a composition. And at the end, that's going to give you features, which you are going to make. I mean, classification, you can use those features for anything. For classification, for detection, or semantic segmentation. Okay, so this final layer, as I said earlier, it's like a simple, fully connected layer, which is a multi-layer perceptron, and we just discussed this in the previous lecture. So the extracted features from the image are treated as input to this MLP, and then we make predictions about like what, let's say, image classification, what object is present in these set of features. Okay, these are also called feed-forward neural networks. Now, so that was like a brief overview, and we have also seen this learning process, the whole pipeline, how we train these models. So again, we don't train on like single images. We have like the full training set, right? Given a huge data set, we split that into training and testing and validation. So these features in case of CNN are extracted by that CNN part. Okay. So this CNN part will give you these set of features. So this, I think we just covered in the previous lecture, like what's the difference between neural network and convolutional neural network. And one big difference was neural network actually worked on flattened set of features. We don't preserve the spatial structure. In CNN, we are preserving the spatial structure. So that's one positive. The other is like, while we are doing that, we are able to actually share the weights. So which reduces the memory consumption of the network. And later we will, when we do the case study, we'll see that like how that reduces the amount of weights we need in a network drastically.